defense of Nadya Serebriakova. Nadya Serebriakova has presented to the faculty the PhD thesis on the topic probing internal and atmospheric physics of massive single and binary stars in partial fulfillment of the requirements for obtaining the degree of PhD in science, astronomy, and astrophysics. Nadya Serebriakova shall now publicly defend the PhD thesis. Nadya Serebriakova, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. I now give the floor to Nadya Serebriakova.
Thank you very much. We're going to wait for a couple of seconds to my phone, which is probably already now. Okay, thank you very much for coming today for the defense for my presentation. And yes, indeed, as the chair announced, we're going to discuss internal atmospheric physics of massive single and binary stars, which is probably the most vague title you've ever heard for PhD, but don't worry, you'll get to understand why it is so in a couple of, in an hour. Oh, yes, it's called rounding. So, why massive stars? If we look at structure of stars of different masses, we can notice a large difference in particularly large mass stars, high mass stars, because of their heat transfer. Stars of lower masses, they have convective envelopes, which means a lot of mixing, movement of the material in the outer layers of the stars, while the massive stars have convective core, and well, the mixing happens there, but then we have a radiative envelope. And this is what makes these massive stars interesting, because if we look at the zoomed view of this internal structure of a massive star, we can see what layers it constituted of. In the center, we have a core, which has this convection and mixing. Then we have a radiative envelope. Between them, we have a core boundary layer. And then, in the very outer layers, we have photosphere, which actually we can observe. So it's the outer layers of stars that we can directly see. But then, underneath it, in the layers a bit deeper that we can't see, we also have a subsurface convective layer. Why it is important is that this particular structure allows for propagation of waves, of pulsations. And don't worry, I'm not going to discuss any seismology pulsations here today. It's just important for context that these stars and their radiative envelopes allow for probing or studying really deep interiors, because in these radiative layers is where the waves can propagate, so we can actually reach a deep in star, and by doing seismic modeling, we can infer some parameters from actual interiors in stars. While for stars of lower masses, where we have convective mixing in the outer layers, it's actually where pulsations can also happen, but then they don't penetrate, say the outer layers. So basically, what makes the stars, the massive stars, unique is that we have unique means of actually looking inside the stars. But, one important note though. How do we know if a star, a random star that we observe, has this structure or not? Actually, it's quite simple. We have a very convenient diagram for this, HR diagram, and I will refer to this many times during this presentation, so let's just spend a couple of minutes trying to explain how this works. So basically, if we put any star on this axis, where on lower axis, on the x-axis, we have temperature, which is basically just a color of star, where the right part means cooler stars and the left part hotter stars. And then on the y-axis, we have how bright the star is. We can see that most stars, they would lie on this thick curve, which we call main sequence, and that's where most stars spend most of their lives. And basically, if we take any star, we measure how bright it is, and we measure its color. We can put it on this diagram, and we can see directly what initial mass it has, and then we can guess some things about its structure. So, for example, if we know that the star is very bright and very hot, we can immediately see that it's a very massive star, and then we can guess that, yes, it has a structure with the convective core radiative envelope. But of course, it's not the only properties that actually affect the properties of star. It's just the very basic ones, the most important ones. We also have other things, such as chemical composition of the star. And depending on how much of heavier than helium, I guess, that's what we call metals. Everything that is not hydrogen, not helium, we call metals. So the properties that we call metallicity, it also affects the evolution of the stars a lot. And here, for example, you can see this HR diagram copied 6 times, basically, where the columns represent different metallicity, different amount of metals that we have inside the star. And then we can see that in these green shaded areas, these are theoretical predictions of where these very important pulsations can be excited that we can use to probe deep stellar interiors. And we can see that it actually covers a large space in higher metallicity, but in low metallicity, these pulsational instability regions, these green shaded areas, they almost disappear. So the question is, how do we calibrate these stars? Because here, yes, we have astroseismology, a very nice, great tool for calibrating internal structure, but what do we do with the stars when we don't have pulsations, when we don't expect pulsations, which are these low metallicity stars? And that's a large focus of my PhD thesis, actually. What do we do with these stars? So, of course, the first question is, are there actually not any pulsations in this region? So first of all, we need to check observationally if we see any pulsations in this low metallicity or not, because then it would be very interesting to see if the predictions somehow deviate from reality. That's always the funniest part, right? So yeah, don't bother about this slide being so empty. It will fill out further as we go through the presentation, right? But now the first goal. So for now, we need to check whether there actually are or are not existing pulsators at low metallicity stars. For that, we run observational campaign. So we run observational campaigns to check the things, and here what we're looking for is a sample of stars in LMC, which is just another galaxy which has lower metallicity, this lower content of metals. And then if we observe stars in this environment, we know that they're low metallicity, and then we know that if we find pulsations there, it's something fun. So we selected a sample of stars from this LMC galaxy, and we followed up with spectroscopic observation, which is, as we will discuss further in several slides, a nice tool for studying in details the atmospheric parameters of stars, the outer layers. And yes, we were granted observations and spent like hundreds of hours observing this program. But then, if we want to check if there are pulsations or not, we need to look at the light curves, which is variability of brightness over time. And if we see some periodic brightness changes, this may be pulsation. So we would search for this. And we looked at the light curves of the stars observed from the satellite. And unfortunately, there were no any pulsations. So yeah, that was my face when I actually spent a year trying to find these pulsations in the LMC. But actually, it's very understandable because when we perform spectroscopic analysis and derived parameters of the stars, it appears that all our LMC sample, which is the upper part, they already passed their main sequence stage. They're already too evolved for actually exhibiting these pulsations. Because probably, as you remember a few slides before, when I showed the shaded the green areas where pulsation may be extracted, they were just skips across main sequence, basically. But our sample is too evolved for this. And this lower part is actually from our galaxy. It's not from MC, so it doesn't matter what happens there. Not for me. So yes, it's concluded that in this sample we don't see anything. It doesn't mean that there are no pulsations in there. It just means that we selected the sample poorly, and this needs to be corrected in the future. But for now, we need to do something still about our current samples, current low metallicity stars, and then we want to search for alternative means to look into these interiors of the stars. And as I promised, for this we need to dig a bit deeper into spectroscopic tools. So spectroscopy is a technique that allows us to measure how much light we receive at every wavelength, every color. And then when we look at this spectra, this amount of light that we collected from different colors, from different wavelengths, we can see that it looks very differently depending on which parameters of the star that we look at. So here in the upper part, we have hot stars, and we see that there are not this many spectral lines. It's basically just a couple of very broad dips. But then as we go cooler in temperature, or rather in color of star, we can see how many more lines we have and how more narrow they become. And that actually allows us, by measuring this spectra of stars, defining very precisely characteristics of the stars because of how this line is structured and what are the parameters of the profiles of these lines. For example, these line profiles, if you take one single line from this any spectrum of the star, we can see that it can be affected by many different things. The very narrow internal thing, the very narrow line in the center as a solid line, it shows internal profile of a line, which is basically defined by physics in the atmosphere, defined by parameters, by temperature, by surface gravity, and it's defined by some line parameters of the transition in atoms that we observe the line for. But then different velocity fields in the atmosphere can probe this thing. So the center wavelength is supposed to be fixed for a single line because it corresponds to energy that is required for atom to have transition between their energy levels. So it should be fixed and very narrow. But then we have Doppler effect that allows changing this wavelength of energy slightly. And this photons of a bit different energy can still be absorbed. So if we have velocity fields, some large-scale motions in these layers where the spectra are formed in the atmosphere, then the lines may appear much broader than this internal function. So one of the most common mechanisms of how we can broaden this line profile is rotation, because all stars rotate. And of course, we have one part of the disk that rotates towards us, moves towards us in the orientation, another part of this that moves out in the opposite direction, and then this means in Doppler shifts that one part of profile shifts toward blue color, another toward red, and then we have these broadenings that allow us to determine the velocity of such rotation, because depending on how much broader the line became, it means the velocity of the rotation was larger. And then, of course, we have another mechanism, this microturbulence, and don't get scared of the name, it's just a weird name that we gave this profile without even knowing what it is. Yes. Can I take a picture of this? So this profile is denoted as the dotted line. And in contrast to the dashed line that represents rotation, you can see that it's more triangular, it's more narrow. While rotational profile, which is the dashed line, is more round. And this what allows us to look at the profile and say, okay, there's something else happens that is not rotation, but it also has the similar scale of hundreds of kilometers per second. So it's a large scale velocity field that we don't really know what it is for these massive stars. And two dominant possibilities of what this could be are that they either form in almost outer layers, or they originate from the convective core, and then via waves propagates to the surface. And that would, if it would be true that convective macroturbulent velocity originates from these reactive waves from the core, it means that we would probably have a mean to look at the interior by studying the properties of this macroturbulent profile. But first of all, we need to know what it is actually. And in our sample, we tried to look at these macroturbulent profiles and see how what we can get there. And first things that we tried to do is to determine different projections of how different projections of velocity contribute into profile. But it appeared that variations in this theoretical profile are too small for our observed data quality to actually say something about this contribution of different projections of velocity. And thus, this method couldn't be used on our particular sample. But anyway, let's just skip it quickly. Another thing, if we just take the absolute value of this broadening, so basically the width profile, macroturbulent profile, and put it on the plot from this luminosity, which is the same measure of brightness that we use in the HR diagram. So if we just put a plot of this, an x-axis absolute value of the velocity, in this outer layer some macroturbulent velocity, and y-axis we have luminosity, the brightness, we can see a very nice, for an observer, a very nice trend of having a turnover at some point around like 3. We have a turn where suddenly we have large macroturbulent velocities. And also you can see nice gradient in color. And here color of the symbol means temperature. So we can see also dependence on temperature some. And also you can see that triangles and circles are located in different parts of this plot. So what are these triangles and circles? You probably noticed that here we have much more points that we showed in the, probably you didn't notice, but much more points that we showed initially in the HR diagram where we showed the parameters of our stars. It's because we actually extended our sample. We just included some values known from literature, from work of Simon Diaz, and because he also measured the macroturbulent velocities, and then we only use the absolute value of macroturbulent velocity without bothering about the sexual components, projections of different projections contributing into profile. We can just take these measurements and compare it to ours. And it has a very nice coverage in the parameter space. You can see this nice spread of points across the cell diagram. But the problem is it's not from LMC, it's from the galaxy. So the metallicity there is normal. But still, it's interesting to compare with our sample from LMC. So yeah, here you can see these triangles that are taken from these galactic samples, and circles are from our LMC sample. Regardless, we looked at these nice trends and we thought that maybe if it's so prominent, we could see from models if we can describe it by any velocities that we see in models. And somehow the MESA models, MESA evolutionary models, gave us convective velocity in the subsurface convection layer. So if you remember this model of stars with the convective core and radiative layer, there was also a subsurface convective layer just beneath the surface. So if we take model velocities, convective velocities in the subsurface layer, and plot it on the same diagram, we can see the very same nice trend with the turnover at some point and the very same shapes, the very same gradient in color, temperature, and the symbols also have the same niche location. So what this means is that we can actually see that macroturbulent velocity, this weird unknown profile shape that we see in our spectra, it actually corresponds well to model velocities in the upper layers. So it's likely not originating from the inside the star, from the convective core. So unfortunately, this kind of closed the route for us to use these macroturbulent profiles as calibrators of the interior system. But still, we wanted to extend this check and see one more thing. And this is like whether these are convective, subsurface convective layer. So here is the models of stars. And x-axis is basically age. In y-axis, it's enclosed mass. So below 0, it's the very center, the core. And then the very upper part is exterior layers. And the hatched area is just radiative transfer, and the color, the black area, is convective transfer. But then, we can see the convective core, of course, but then if we zoom in very, very external layers that we can't even see in this plot, because it's basically like 1 pixel in the very up. If we zoom in into this subsurface region, we can see that these convective velocities actually reach quite large values of tens and actually up to 100 for some stars velocities. And that's what we think might be actually connected to how macroturbulent form. But what we also can check is whether, if still somehow, macroturbulent profiles were originating from the core, well, the thermal gravity waves originating from the core and transporting to the surface. We can see if this convective layer would stop penetration of such waves or it would allow it. Because convective layers, they serve as basically walls for waves that propagate in this radiative region. So we can try to see whether this layer is thick enough to be actual wall or the waves could still penetrate. So we briefly looked at it and we saw that actually for a majority of our stars, especially for all stars in LMC, from the models, from these 1D MESA models, it follows that this layer is strong enough, thick enough to prevent penetration of waves. So it's again one more evidence for macroturbulent profiles to be originating from convective layers, subsurface convective layers, rather than anything inside the star. So, unfortunately, this path of client profiles as calibrators for interiors failed. So we moved to the third goal, which is try to find another alternative means to alternative means. And this time we moved to binaries. And this may look as a bit random switch, but honestly, binaries are just same stars, just that they orbit in couples. It's same massive stars, same structure, same physics. It's just that they are born as a couple and they orbit each other. What it gives us, and why we are interested in them, particularly in this in the context of my thesis. So, first of all, if you look at light variation of the stars, we see that due to this orbital motion, the stars may eclipse each other. And if you look at change of their brightness with time, we can see dips when one star projects onto another. And depending on morphology of these dips, on their location, on their shape, we can determine a lot of parameters about the orbit of the stars, about the stars. So it actually gives us a lot of constraints about these stars themselves. But also, if you look at the spectrum, their spectra are, of course, a composite of two spectra of stars that we looked at like a few slides previously. Now it will be two spectra of two stars overimposed, but then shifted due to the same Doppler motion. But this time it's due to orbital movements at different phases. If we observe spectra of stars at all these orbital configurations, we can actually see how their lines shift depending on which phase we observe the binary at. And then if we measure the shifts, then we measure velocities of their orbiting, and then from orbital mechanics we can determine masses of such stars with very high precision, which is great. But then, again, what is interesting for us in context of our thesis and finding this alternative means to alternative means is that there is a problem there. If we take a mass and measure it dynamically, but then we do the same as we discussed before when we measure brightness and temperature of star and put it on this CHR diagram and looked at which mass region it corresponds to, we can see that these two estimations will be different in many cases. And this is a problem that persists for several decades now. That here is an example of an extreme case. It's not always this strong, but we can see that this star was located according to models at like 17 solar masses, but then the dynamical masses from this binary dynamics gives 14. And they're very precise. But also the tracks on the chart diagrams, they also were tested quite a lot. They're commonly used, so can they be this wrong? The common explanation for this is to include extra parameters in this boundary between core and convective core and radiative envelope. This overshooting, which is basically extension of the core further. If we adjust these parameters in models, we can make the tracks, the evolutionary tracks, to match dynamical masses. But then the parameters that we need to implement there is huge, it's enormous. So the question is, how much of this famous problem of mass discrepancy is actually determined by these coefficients that we don't include or include in models, and how much it is something else. Maybe it's originated from methodology. And for that, of course, we again need to observe a large sample of stars. And happily, we have access to the Hermes spectrograph, so we could run a large program to follow up known eclipsing binaries and observe them at very specific phases to completely cover their orbits, get the spectra at all phases, so we could very precisely measure these shifts in the spectra and determine masses. So we run this program, and by now we already have hundreds of stars observed, and now we need to analyze. But then there's another problem, that the classical way of analysis of them looks something like this. No, I don't expect you to understand this. It's designed to be confusing. The problem is we have these very different observables. We have light curves, we have spectra, and we analyze them separately. We analyze separately the shifts in the spectra and the spectra of the stars themselves. And then we need to somehow make all these three things match. Four things actually, but whatever. We need to make them match somehow, even though we use different parameterization for each of the methods. But all these parameters are connected because we still observe the same system, it's just the projections are a bit different. So the classic approach is a bit of a mess that requires a lot of iteration and often is done by different people, even because spectroscopist is often a different person than a modeler of light curves, for example. But even if it's the same person, one person can analyze several objects within, like, I don't know, weeks maybe, and then it's very common to publish one paper per object. So the exploitation of data goes very slowly because of this process. And then when we try to compare different results from different authors, we have a lot of biases between these results because people use different methods. And then we don't know how much of this math discrepancy problem actually is because of these different methodologies, different methods. Because the largest mapped math discrepancy sample is like 30-ish stars now, and it's a compilation of different authors. So we don't know very well how much these different approaches affected the results there. So what we needed to do is to develop another method. Well, not another. To improve the current method a bit, to get rid of these iterations, to get rid of different parameterizations for different observables, and instead merge all these observables into one system and one set of parameters that would be used to model all different parts of the data. And then we need to automate it, so we could use it on this large, for a spectroscopy sample of several hundreds of stars. Right? And that was my work last year too, I don't know, somehow. It was to develop this another approach to analysis of classic eclipsing binaries. So the problem with trying to analyze all these data aspects simultaneously is the weighting issue, because we don't know how much we should trust our light curve, how much we should trust our spectra, and then if we try to connect them, should we say that, okay, it's probably space photometry, it's so much better than our whatever we normalize in spectra? How can we do this? How we determine these weights? But luckily, I'm known for loving self-balancing systems. So I thought maybe we could do something similar and design a system that would balance itself. And when we don't need to actually apply this manual weights, and instead find okay, I see people take pictures, so I'll wait with these, switching to the next slide. So I thought that we could develop a system where we don't have to manually balance different weights, different observables, and instead it would do it itself somehow. And luckily, mathematicians have a solution for everything. And like for 2 decades already or something, they have this very nice method of multi-objective optimization, which essentially is a way to, instead of iteratively going from one to another observable, or instead of assigning weights to different observables, we can simultaneously do optimization in all dimensions, in all the observables. So basically what you need to do here is just to imagine your normal like 15D parameter space and then project it into 4D space instead of 1D space. That's all. Probably it's better after like reception. But yes, it's not much more to say here, except that by design, this method means that we would try to search for trade-off function, trade-off surface in our objectives. And this means that we don't have a single best solution. We have entire surface of solutions, and then the users themselves, they would have to actually make a choice on what solutions they would get. This would, again, either mean assigning weights and then selecting the minimal distance one in this weight, or using some other methods. But for us, it's luckily good because we can look at the entire surface. We can see how the parameter space behaves, how the objective functions behave in parameter space, and we can see relationships between different dimensions. So it's a very useful way of actually estimating what we are doing, even if it doesn't give us this nice automated answer. It still allows us to do a step forward compared to classical methodology, where we just blindly bias ourselves toward one direction, one point, and we don't know what happens everywhere else. But here, with this approach, we can basically map the entire space of objectives and then do whatever we want with it. So for us, what helps is that for our particular study of mass discrepancies, is that we can actually, slides back, we can actually take a look at how this parameters look like, and we can color it based on how much mass discrepant the solution is. And then we can select solutions that are closest to models, or we can select solutions on some other metrics, or we can analyze a full sample and then do statistical measures of discrepancy among the population of solutions, and then map it on the HR diagram and see how it corresponds to models. So we can do a lot of things with it still, even though it doesn't provide us with the immediate one best solution. Anyway, just as one of the examples of result, as my favorite showcase for now, just because all the other showcases are basically tests on synthetic data that are absolutely boring, or tests on very well-known systems that are also boring. And instead, also my favorite one is this extreme example mass discrepancy star that I showed in the beginning of this problem. And because our program, our code, is designed to search for large, for a family of solutions, for different solutions, we can see different local minima, and one of these minima actually corresponds to solutions that doesn't have mass discrepancy, or at least not this dramatic mass discrepancy as was reported earlier. But then we looked at, well, actually one of co-authors pointed out that there was a bit earlier solution that was from like 2004, which I missed because probably it's too early for me. I don't know, I was 8 at this time, ages ago. So I didn't know that this solution exists, but when the co-author pointed out, and we were plotted without solution, and they aligned nicely with the circles. It was a nice blind test for me to see that these solutions that we receive are actually not total crap, and they may actually be valid solutions, even though they're in local minima. But at least they don't give us 3 solar masses of mass discrepancy. So it's a nice thing to have. And just it's time to come to, yes, it's time to come to conclusions. Great. What's next? Now, when we have this framework and it's somewhat tested, now we need to apply it to a full sample, but of course it takes time because running this optimizer takes time. It's like a few days per one target. So it will take some time for us to analyze a full sample, and hopefully in several months from now, we'll have more definitive answers about mass discrepancy and about the role of these biases in our techniques, in our modeling tools. But for now, I'll just review that and say that it's a work in progress. And of course, it's this design, this multi-objective optimization, where we can include different observables in one framework and connect them and connect parameters so they are self-consistent. We can actually add more observables. We can add seismic frequencies. We can add, I don't know, astrometry data. Why not? This would allow us to constrain these systems even more, and probably would allow us to select best actual solution, maybe. So that's another thing that we're looking forward to, is actually trying to include extra ingredients in these models. And meanwhile, while we have this floor, I would like to thank all the developers of the code who make them open source. It's such a nice thing to just have access to nicely documented, well-tested, well-written code, and just be able to use it. So shout out to these amazing people who wrote the best codes I've ever used, probably, and I use them a lot in this work on the binaries. And I would like to end our presentation with this.
Thank you, Nadya. Now, let me first introduce the member of the examination committee. First, we have online Coralie Naylor from Lysia in France, who was present also at the preliminary defense and has been following online today. Then here in the room, we have Ignacio Ribas from Institut de Ciencias de l'Espace in Spain. Then we have Uxana from the Institute of Astronomy and Astrophysics. Then we have the two supervisors, Andrew Tkachenko and Koniat, also from the Institute of Astronomy and Astrophysics. Excused today are Tom van der Solaar from the Department of Mathematics, who unfortunately is enjoying public transport at the moment. He did his best to come here, but unfortunately it did not materialize. As well as Peter de Cat from the Royal Observatory of Belgium, who was planning to be here, but was faced with an emergency that he had to attend this morning. I am myself, Thomas Elias Kokolius, from the Institute of Nuclear and Radiation Physics here at the KU. We will now proceed with the question to the candidate, starting with online Coralie.
Good morning, everyone. Can you hear me well?
Yes, I can hear you, and the jury can hear you. I don't know about the back of the room, but it doesn't matter.
Okay, I will try to speak loud enough then. First, apologies for not being able to be with you today in Leuven. Unfortunately, I had some commitments in Paris that didn't let me travel, but I'm happy that I can at least follow online. So thank you, Nadya, for this clear and very pedagogical presentation, which I think nicely showed the breadth of your PhD work, because you've done really a lot of different things. And we could see that in your presentation. So, of course, I have some questions. And so my first question is about your work on binaries that you just described at the end of your presentation. In this work, you have assumed relatively simple stars. Of course, they are binaries, but I mean, each of the stars in the binary is relatively simple. It's non-variable. It's a stable star. So I was wondering if you're planning to extend your new technique, this repair code, to more complex cases, such as pulsators or magnetic stars, maybe. And what would this involve for your code and for your work? And what would it bring to your studies?
Thank you for the question. So about magnetic stars, I'm not sure we need to discuss this. But yeah, let me first answer about pulsation. Yes, we are planning to include this, but currently we are still deciding on architecture of these inclusions. So there are two ways. We could either include already measured frequencies as extra objective, or we could directly change, instead of modeling, as you remember we discussed it during internal defense, we model currently binned light curve, phase folded binned light curves. If you change this, if you just model normal time series, we could probably simultaneously insert the seismic signal and the binary signal. So we are now still deciding between these two possibilities, thinking what would be better, what would be easier to include, or more practical. And yes, this would bring a lot of in our study in terms of physics, because by the way, like 1/3 of our sample is pulsators, so we need to do this absolutely. But also having these pulsators means also having extra constraints on their properties and extra parameters that we would be able to constrain from this. So I would hope naively that it would help us to shrink this parameter surface that we have now, the rate of surface, into some more concise region, one global minimum. But I had these hopes when merged light curves and spectra already, and it failed. It actually became even more difficult to model the system. So I don't know if it will be easier, but yes, it's something to look forward to. About magnetic cyrus, I'm not sure. I don't know much about modeling magnetic light curves.
I'm mentioning magnetic star because statistically 10% of your sample is magnetic, so you cannot really ignore that.
We cannot, or we can just discard 10% of the sample. Yes, but I'm not sure what we see in light curves. Is it like spots, like chemical spots, or is it but then if it's chemical spots, that we also see it in spectra, we also would need to include this in the spectra models too. And right now our spectra are orbit average spectrum, and not the spectra of the separate phases. So I'd say actually modifying the spectroscopic part would be more difficult from the point of including magnetic effects. But yeah, yes, something that worth working on and worth discussing for sure.
Excellent. I'm looking forward to your future versions. Okay, so my next question is about the code repair that you developed. So when you developed it, of course, you tested it very extensively, and you didn't mention too much this today, but you did do a lot of tests. And for this, you used simulated data that you computed. And in your simulated data, you've used an equidistant phase sampling. And of course, in real data, the phase coverage is often not that regular. And so I was wondering about the impact on your result of a less favorable phase sampling, the real sampling in observation. So can you quantify the minimum sampling requirement for your repair technique to work? And can you give future observers some kind of guidelines of what they should acquire?
Well, the sampling that we use is 8 epochs per orbit. Was actually tested already in the work of my supervisor and Kazimir Pawlowski, who tried to perform disentangling based on this minimal amount of epochs, and it works well. So I think it will be also enough for our case, because basically what we need from coverage is the spectral disentangling, right? Both effect it imposes is that our solutions, of course, are less confident if the phases, these 8 epochs or whatever, they didn't appear in extremes of the orbital configurations, because then we have the best constraints. So it's not so much about the sampling in terms of number. It's more about which phases we sample. So it's very important to observe exact phases. That's why this program is so painful for our observers, but I think they manage very well. So yeah, that would be my answer.
So you need to know the orbital period very well in advance to phase constrain all your observations. But 8 observations is enough if they are well placed. That's your conclusion.
Yes, I think it is my conclusion. And luckily for our sample, we have nice light curves from TESS. It's program designed to follow up TESS light curves of eclipsing binaries. So the parameterization of which phases we need is not a problem. But of course, for planning future future missions, missions programs, it is important to, yes, look at existing data and see if there is information on orbital parameters.
Again, 8 observation might be good enough for simple cases, but when you will move on to pulsators or magnetic star, you may have to also sample other periods in the star. So then it might not be enough anymore. So for the future, also think about this maybe.
Yeah, but it depends what effect we want to sample. If we want seismic profiles, and yes, of course, we need very small cadence, large cadence, what is very tight observations and very long time series. Yes, it of course depends on the goal of our sampling. But for simple orbital solution, I think 8 would be enough.
Thank you. And my last question is more about the future work that you may do maybe. What do you think that future instruments or space mission will bring to your research field? And what type of new data would you really like to get to be able to progress in your field?
I knew you would ask this question because of Plato, but I'm still going to answer not about Plato. Even though Plato is nice, okay, Plato is nice. We'll observe more bright stars, larger field for 2 years straight. Great for seismology. But since I'm not yet doing seismology, it's not this important for me, as I'm more looking forward into launch of space spectrographs. That would be my, I don't know, my supreme goal of having this very nice spectral data from space.
So why would space spectra be better than ground-based spectra?
Because again, long-term series, if we want to sample this pulsational variability, for example, and this what is CubeSpec working on, well, will be at some point, hopefully. I don't know, I look at it, he's very optimistic. Yeah, it's a pity you're not with us in this one. Anyway, so it is important that we can do uninterrupted observations for longer than one night, and why night with good weather. So that's an important factor, but also it's atmospheric absorptions, because from underneath the atmosphere, from ground observations, we can't observe certain parts of spectra, such as far UV even. So that's also a very nice advancement. If you launch a space spectrograph, we can do far UV, and that's important for hot stars.
Okay, thank you very much for this discussion.
Thank you.
Okay, thank you very much, Kohali, for your questions. We now move on to Vikas.
Okay. So I second Coralie's comments about thanking you about the quality of your presentation. I think it's been really clear and very pedagogical. And so it's clarified many of the things that might be not so clear sometimes from a written text. I also like to praise your work for this for your thesis report, which is very nice and it's really enjoyable to read as well. And you might learn lots of things, and particularly the binaries, which I soft spot for, so that's very useful. So let me start. Let me ask you some questions. And let me start by a fairly general one. Both in your presentation and also in your report, you talk about a little bit about overshooting, convective overshooting. Yet when you actually analyze some of your observations, you said, or you use your models, you set the overshooting turned to mostly 0. And is that because you're neglecting overshooting, because there's nothing you can learn from studying it? Is that it does not affect your conclusion? So what's your final conclusion on whether overshooting is relevant or not for these kind of studies?
It's because we didn't focus on this overshooting yet. We used the models for these external layers, not core overshooting. It doesn't this relevant there, right? So in this study where we showed models, we didn't include minimal overshooting because it didn't matter for us much. But now with analyzing binaries and mass discrepancy problem, we will have to do this. And then of course, when we do the observational mapping, we will have to compute models with different parameters of overshooting and probably different profiles, not necessarily this linear step overshooting, right? So yes, we will do this, but it's beyond the scope of this research for now.
Yeah. And some of your binary components are involved enough for overshooting to be affecting, let's say, the position on the edge. Okay. Can you show us? I think there's a slide where you show your sample, your LMC sample, the Gabruer sample, and the Simon Diaz sample. So whichever, yeah, you just the one has the HR diagrams. No, the HR diagrams. Yeah, there you go. Yeah, the one just the one before.
You have a delay. Look at my.
Oh yeah, sorry. That's yeah. Okay, then when you compare this, the left plot with your initial plots about where you expect pulsations, of course, you're not covering the area where you're expecting pulsations. So what is the limiting factor? Why you don't have targets there? Is it brightness, but spectroscopy or photometry? Why don't you have stars that would allow you to see pulsations on the LMC?
Yes, it's mostly because of our spectroscopic limitations. Even with the US that is mounted on 8-meter telescope, we have limited brightness and reachable, and these targets are in LMC, so it's far away. So that was a limiting factor, so we couldn't observe weaker targets, lower. And the fact that we didn't have anything with more to the left, I think is just a coincidence. I don't have any other explanation for this, honestly.
Do you expect, for example, with new facilities, it's a follow-up question, that you will be able to sample this region and then effectively see if there's any pulsations in the LMC?
With what?
Future facilities like here.
Yeah, extremely.
You mentioned ground-based or space, it's going to be huge spectra also on the ground coming up. So
yes,
is that something you...
But also remembered why also maybe bias is also because the sample was based on detection of stochastic low frequency variability, and it's present in supergiant. So that's why we also have this bias toward this region too.
And photometry is also an issue here, right? Because of that. So that would be because test limitations as well on this. Now you thought you'd only get one question on Plato, and here's the second one. So is Plato going to solve this in some way? It's in the Plato field south has also LMC.
But it's brighter targets, right?
So it's not going to provide any deeper targets there.
Not sure. I don't think so.
And one more question about missions, or not future, but current missions. This is something that I've been wondering when reading your report and everything. You didn't mention Gaia at all, right? So Gaia is providing parallaxes, and in some years, and also provide epoch astrometry, and therefore lots of other data. Is there anything that you can use Gaia for in your analysis? There's something that you could find a use for these very precise parallaxes that Gaia is providing, and maybe further your analysis on some of these?
Yes, of course. So it's very useful to have distance known from parallaxes, because then we have basically a constraint on luminosity too. From in our binary analysis, that would be a large contributor, given that we have entire families of solutions and we don't know how to choose between them. Gaia could help us to do this by providing distance.
How about Gaia binaries? We expect many of them in a year and a half or so. Is this going to do something to your sample?
It's too many. It's too many. I can't do this millions of this spectroscopic follow-up, right? It's very important for us to have spectroscopic follow-up. So it's a too large sample for us. We could probably follow up some, but yeah, I don't think it would be a large game changer compared to what we already have in TESS, which is also thousands of binaries.
We have time for one more question. Can you go to slide 32? I'm using the right way to get to slide, I guess.
This one?
Yeah, this is the one. So binaries, of course. So I understand that from your analysis, you end up with a bivalued solution. So you could either have a hotter or a cooler solution. Here you plot the cooler version solution, and then you came up with a paper that 20 years ago more or less predicted the same kind of solution. So my point here is the main issue here is not with the fit of the binary data, meaning Lake curves and real velocity curves, but it's mostly temperature determination, right?
Yes.
That's where the main issue is more than. Okay. So again, is this, and I understand that from your solutions, you also get a hotter solution in your fits, let's say. Is there a way you could actually, because I understand you don't make a call in your report about which is the one you prefer, or at least maybe it's here, maybe it's the one you showed here. But is there any way to really discriminate from the other? Because in your when you described this, you also said that the user in your Pareto, let's say your multi-objective minimization, is the one that finally makes the decision, right?
Yes, exactly. That's the main message, that this method alone can't allow us to choose. It doesn't give a determinate answer. What we need to do is to attract some extra information. So for example, again, Gaia would help, or including some extra constraints. I don't know, seismic analysis maybe help, but again, I'm skeptical. Anyway, so yes, basically we need to include some extra constraints such as Gaia, and then we would be able to probably distinguish between these two, but for now we don't want to state that we prefer any solutions because there is no actual reasons to do so. Yes, I prefer this one because it less deviates from models. And I don't think the model would be this much wrong. So for me, it's already strong evidence that this solution with lower temperature is better. But it's not enough to be 100% sure.
Okay, and just one very last one. You have a repair code that is very nice, and I don't think, maybe I missed it, but you didn't say anything about it being public or making it public. You have plans to, and
there is a GitHub link in this, I think, but it is going to be public, but for now this GitHub repository is private because I didn't write documentation. That's what, like, the only step that I need one more step to publish this. It's like writing documentation, like how to install all this nightmare of different codes. And so yes, it's going to be public. Yes, it's from my very beginning. Yeah, it's my strong attitude that all codes should be public.
Thank you very much.
All right, so apparently I have to jump in immediately. Can you go back to slide number 17?
17.
And I know it's not your work, but this plot puzzles me for years. Let's, oh yeah, another one, but that doesn't matter. Let's look at the right hand one, the one that is fully populated. Beyond the mean sequence, there's many blue supergiants that are staying there, being observed there. The transition through the Hertzsprung gap should in principle be extremely fast, and that region should be mostly empty. I know it's a work for just some ideas, but you've shown it. I was wondering whether you had yourself an insight about this problem.
Well, I think it was just specifically designed to like populate equally the sample when they observed. They were designing to equally populate the HR diagram. No.
But what I'm saying is that those blue supergiants that are past the turn should not exist, or should not stay there for more than a few hundreds of thousands of years. So there should be very few of them, even in the gas.
Yeah, but we have selection bias. We intentionally select them to be in the sample. Well, not we. 70 or something. I don't know.
You also have a new block, right? In the LMC, there's a lot of blue supergiants that are post-turn off.
Well, it can be that our parameter determination is not perfect, and it's actually shifted. But for like all stars and all different orders, I would doubt this. Can we be wrong about predicting these short living ages? Maybe, I don't know.
So to me, if it's truly there, it means that there's a physical process that stabilizes them. because the lifetime in that region, which is around 15,000 Kelvin or so, 20,000 Kelvin, but if you are post turn-off, the star is not in, it's outside the equilibrium. There's no nuclear reaction in the core anymore, and it can be very quickly red supergiants.
But still, we didn't do any bias corrections, right? We don't know how relevant this overpopulation is, given that there are millions of stars that we didn't put on these diagrams, that are not on this region.
Still disagree.
Okay.
I think it's an open, I'm not asking you to solve it. I think it's an open problem.
It is.
I've been working on those stars, so I was wondering whether you had an insight. Can you go to the next slide, I think? No? The one where you have the big red and blue dots is no proof.
Big red and blue dots. This one.
Let me lay out two physical quantities in front of one another, and then I'm going to ask you to comment. The first one is the microturbulence speed that you get on the order of, at least for some stars, so the order of 50 kilometers per second, sometimes higher. The second is that the sound speed in the atmosphere of those stars is around 20 kilometers per second, or a little lower. Right?
What was the second again?
The sound speed, the speed of
Sound
sound.
speed, yeah.
So that would make the microturbulence supersonic.
No.
So can you explain this discrepancy?
It's not supersonic. So if you look at the appendix, we actually plotted these velocities, convective velocities, but they are essentially maximal convective velocities. They're the same order of magnitude, right? We plotted them as a fraction of sound speed, as it's not supersonic. It's like almost it's approaching like 0.9 maybe, but it's not supersonic.
It's not supersonic in the subsurface convection region, not at the because the atmosphere, the velocity sound speed.
Yeah.
That's good. I did not realize that.
Yeah, we check the subsurface convection.
Which is right. I think that's what you should do. I mean, it only matters when the velocity field is.
Yes, but then why we observe this field in the way upper layers, right? Because it's observed, it's way upper than the subsurface layer. So it still matters. But yeah, it's interesting.
And they should not be supersonic because otherwise we'll have shocks and X-rays.
Talk to Dway Payan. I think he has a very strong opinion on that.
All right, next question. Let me disagree with you on the next question, and disagree even more with one of my former colleagues that have been asking me a question just before. You said that binaries are simple stars.
I never said
And I
this.
would like you to list all the physics that makes binary so much more complicated than single stars and magnetic stars.
I never say they're simple.
You did say that.
No, I said they provide masses. That's very nice. I didn't say they're simple.
Can you just elaborate on the physics that makes binary stars different than single stars?
Yes, of course. So, first of all, we have tidal interaction. So their surface is perturbed by this binary interaction, and it can have a lot of effects. Of course, on observational point of view, yes, we can see these effects, but that's not what you're asking about. What you're asking about is its effect on evolution, probably. But then, if they some of them would overgo through the common envelope evolution, and that changes everything about how these stars behave afterwards, right? They could undergo mergers, so it's a lot of different processes there.
Can you link binary physics and magnetic field physics?
Magnetic field? No. Well, I don't know. For me, maybe.
Let me go back to maybe one of my final questions. At some point I need to stop. So you've been looking at stars in the small and large mass clouds at lower metallicity environments. And one of your conclusions is that there is no pulsations.
In our sample,
In
not
your
in them.
sample. So yeah, that's what I wanted to explore with you the breadth of the conclusion. Is it because of the sample selection, or is it because the low metallicity we really should not have?
It's for our sample selection, I think. And also, it's not necessarily if we don't see it, even if we had uniform coverage of HRT. It just could mean that these amplitudes are lower that we can detect currently. So we don't exclude these possibilities that there are pulsations there, and specifically not from our sample that is way too evolved. There are still, by the way, stochastic low frequency variabilities there, right? And well, it can be pulsations in a way, just not coherent.
It's unpublished, there's no way you can know about it, but we have a sample of OB stars in the small margin cloud studied through spectroscopy with 20 to 30 epochs spectroscopy, and we do seem to see variability which we cannot properly interpret as being due to binary. So those are mean sequence stars, so they are pretty kind of.
That would be nice, use these pulsations.
What would you do?
Well, I would first exclude all the other possibilities, like UC profiles shapes variability, right? So probably it could be also like winds or something on, I don't know, triples, whatever. So we need to do full-blown analysis of all possible aspects to know for sure that it's pulsations. Because in this case, at SMC metallicity, it's even lower than LMC, and it's even more critical for theory to be like not super wrong about not having any pulsations there. So yeah, it would be a big deal.
Thank you. Before I hand over the microphone, let me congratulate you again on the quantity of your work in the last 4 years.
Thank you.
Very impressed by you.
Thank you.
Well, I would like to thank the excellent jury members. It turns out that Tom didn't want you to leave there without a few words from him, so he sent questions so that even in his absence, another Thomas could take over and share them with you. The first one is a bit maybe along the line that Hugues was concluding with. It's like you didn't find those pulsations, okay? So it was a bit of a sad green monster at the end. But how would you use the knowledge gained in your thesis to come back now that you've done everything else afterwards to your original goal of probing deep interiors with G modes?
Well, it requires completely different study, right? I would go to classical coherent pulsators and analyze them if I were just to probe any interiors. But of course, we can't do this in low metallicity unless Hugues is right about his new sample. Then probably we can do this, and from these line profile variations deduce some seismic qualities, but properties. But if we are to try to find this pulsation, I would select the sample a bit differently. I would not be based on this stochastic low frequency variability necessarily, because honestly it can be anything in low frequency domain. I would base on this mass regime before below 20, 30 solar masses, because we see that there are some velocity fields there, but the convective velocities in the subsurface layer predict kind of zero velocity. So there is something in there. So I would be strongly suggesting focusing on this region below like 20, 30 solar masses, and try to point the telescope there and try to collect samples from this region. So that would be my next attempt, I guess, at this particular search.
Okay, and then another one in your previous examination in the post session. At some point, you said that the method for binary fitting should not be applied to multiple stars. However, could you not use LPV synthesis code for fitting the spectral pulsations, practically filtering out the lines for the components, even in a multi-star system, and that way look at interesting pulsations?
I don't remember the discussion at all.
Apparently, it was in an answer to a question from Kohali.
Okay. Yeah, I don't know. I need to think about this. Yeah, we have too many problems. Like, if we have these multiples, right? We have the drifts and upsidal motions and all this stuff. We need another sampling. We need much more observations for that. And it would all this effort just to characterizing one particular system with a lot of different effects. And all these effects would only make the analysis less certain. So I don't see a large benefit of putting all these efforts into studying one system. For now, my approach is to try to, okay, we can discard some of the systems, I can live with that, but the remaining stars should be numerous, so we can perform quantitative analysis. Yes.
Okay, good. Thank you for your answers to the Toms. Now I'm turning to the supervisors. Do you have additional questions? Yes. Okay. I was expecting this.
Yeah, first of all, congrats, Nadya.
Thank you.
Very good work and very nice presentation, very enlightening. So I wanted to ask a question that is triggered by the candidates, by the students' presentation itself. If you could go to slide 25. Famous guy on plot there, the overshoot.
Oh.
So while discussing this, you mentioned like, you know, the mass discrepancy can principally be explained when overshoot is introduced, but then one has to assume a ridiculously high value of the overshoot. So ridiculously high is not a physical term. Can you please describe it in the context of physics? Why 0.6 is so ridiculously high?
It's what our mass modelers from our team says always. Because it's 0.6, it's a pressure scale height, right? And it's quite a lot. It's quite a lot for extension of just that overshooting extension of a core without completely. I don't know. It just sounds too wrong from normal modeling.
I think the extension is in the right direction to answer this question.
Okay.
Do you mean that at some point, then if you keep increasing that number, you might just end up mixing your stuff?
Why would I?
Is that possible? Would NEST allow you to do that? To end up with a
fully core, like core star, only core, just the core. I don't know. MES allows doing like Tornzhitkov objects. I don't know if we can do entire core star. Maybe it can.
And would that be right?
I would not rely on these models, no. But models can do anything. It's a lot of math, right?
Okay, thank you.
Thank you very much. I will now turn to the audience to see if anyone here in the room has any question for Nadya. Do not be shy. She doesn't bite. She's behind the.
Shy, I bite.
Once, twice. It's dangerous, otherwise I'm going to have to ask a question, and it will be absolutely not related to her work.
Good, and I can see, I don't know, when we're going to the reception. Good.
Okay. Then I will turn to you, and I promised you I would ask a question. It's a reaction I had on one tiny line you put somewhere in the introduction, where you mentioned how those beautiful stars you are looking at eventually die, and explode. And then you mentioned the R process arising from the supernovae. But do they? Have we ever seen the R process of a supernova?
Oh, we see the elements they produce. So it must be something that produces them.
Yeah. Have we seen the R process? Have we witnessed the R process?
It's rapid, right? I don't know. Witness output, I don't know if it was connected to actual events of explosions. But probably I would say that I would intuitively guess, right? as you said, it's not my topic. I don't know a thing about nucleus synthesis. But my guess would be just we can't come up with many other these energetic processes that would, in theory, result to such rapid neutral capture rates. So I would say it's just a matter of exclusion all other not energetic enough processes. And then we think that, okay, it may be this core collapse supernova. But again, I'm not an expert here. I may be saying absolute nonsense.
No worries.
Good.
Good. Okay. Then, if there are indeed no more questions, then I would like to move on to the deliberation.
Andrew, you make it.
Can you tell Coralie to join us back? Can you ask Coralie to join us back?
Yeah, of course. She already left. So I can't.
Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee appointing for granting the doctoral degree in science, astronomy, and astrophysics. Nadya Serebriakova has presented to the faculty the PhD thesis on the topic probing internal and atmospheric physics of massive single and binary stars in partial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics. And Nadya Serebriakova has defended this thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of K. Leuven, I confer upon Nadya Serebriakova the degree of Doctor in Science, Astronomy, and Astrophysics. Now let's go extra. By obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described in the ALEA European Code of Conduct: reliability, honesty, respect, and accountability. I hereby close the session. You may sit down. I believe that the supervisor has to do.
All right, I think it's time for a short speech now from my side, and I hope from Tony's side as well afterwards. But first and foremost, Nadya, well, congratulations reaching this milestone that we all call a PhD. It's an important one, and it's so well deserved. Congrats with that. I don't think it would be terribly inaccurate of me to say that this was a long and winding road for you. And that is because, in your journey, I think you experienced a number of ups and downs, and also your journey resembled to a certain extent the zigzag path. And that's because you faced a lot of roadblocks, but it was very, very wise of you to actually maneuver around those roadblocks instead of trying just to break through with a brute force approach. So that was very wise, I think, and congrats on that as well. That's an achievement, I think. Yeah, and so usually, at this point, I start highlighting the strengths of a student who has just defended, but I wouldn't risk actually to do that with you, because this would be a very long list, and I know how much you appreciate receptions. So I fear I would not survive. Right? So I actually set myself a challenge to pick one or maximum two of your qualities. And I think the very first one I would like to really highlight, and that's your internal strengths. So that's absolutely impressive. I know how many difficult moments you had to go through in the past 4 years, and in my experience, only a strong person internally could actually get it to this stage where we now congratulate you with successful defense of your PhD. And so the second strong point, in my opinion, that is a very important one, is your ability to learn and absorb new knowledge on the fly. So that's absolutely remarkable from my point of view. And just to prove my words, so in the course of your PhD, and not only, but also pre-PhD, you mastered techniques of spectroscopy photometry. You worked with main sequence stars and blue supergiants that are, in the opinion of you, should not exist. you worked with single and binary stars, and I don't know if anyone in the audience will believe you also know what pulsars are, what they are actually doing and what they are made of. So this breadth of expertise is absolutely remarkable in my opinion, and it proves that you can actually accomplish anything in your life. You just need to believe in yourself and you know, set a goal and just go there. Okay? And so again, at this point, I think you will probably know by now that I say a few words in students' native language. Yeah? And for some reason, this language is typically Dutch. So I guess it was just out of the habit that I actually prepared a few words for you in Dutch.
I hope these are not the words that I know in Dutch. Special selection.
Nadя, мои искренние поздравления. Это абсолютно заслуженно. Ты абсолютно заслужила титул кандидата наук. Работа твоя просто замечательная, я считаю. И, как я уже сказал, ты можешь достичь всего, чего ты хочешь. Тебе нужно просто поверить в себя и идти к цели, не видя препятствий. Я считаю, что твои друзья, близкие тебе люди должны брать с тебя пример того, каким сильным может человек быть внутренне и чего он может достигать, какие вершины он может брать. Вот отсылка к драму. All right, so I guess usually people tell me actually that my Dutch is quite understandable. I think today this was the worst version of my Dutch ever. People will confirm. I'm not even sure it was Dutch at all. Anyway, so I think I will just shut up here because I've taken too much time. Once again, congratulations, and I will hand my over to Connie.
I'm not glad I don't have to do that. Okay. My sincere congratulations, Nadya, for your successful PhD defense, and actually, well, welcome to the world of female doctors in science. I can share that with you, and I want to state that because we are both still a little bit of a feminist, right? Because it's necessary. We both are female doctors in science from KU Leuven, and that we share for the rest of our lives. Of course, Andrew is the real supervisor here. I was glad to be a coach from the sideline with some advice, but also as a collaborator for you. And I was particularly happy that you picked up computing stellar models, which is, well, pushing you a bit beyond your comfort zone. I even felt some resistance in having to do that, but in the end you made it work, right? And that's something you should keep in mind. You can make things work, and you have to believe that. So you were scared of doing that. I insisted. You were scared again. I insisted again. And well, being scared is something that I'm now going to have to face for a few minutes. And please bear with me, because there are some words that I would like to share just between Nadya and me. And this is very, very, very far beyond my comfort zone. But I do that out of respect for you. Okay. Daragaya Nadya, Jin Bera Pla, Debia, Nie Prastor. No, Sapasletnie, Shetire Goda, Di Pakazara nam, Shoti Silnaya, Devushka, Sheveraliatnai, Shiua, Dika I Uporostom. Gardziszczem, Jego, Di, Taśtigua, także, jak ja, gardziłeś taboj. I produzoja, i ty, в период также, как и в последние годы. Совместные с вратами и падениями, которые нам всем знакомы. Наша страна этим летом сегодня и помнит. Тудажне в моменте пандемии можно многого величия. Даже если ситуация кажется безнадежной, ты доказала, что умеешь находить решения. Как в науке, так и в человеческих отношениях. Я горжусь тобой, и ты тоже должна гордиться собой. Честно, что всегда будешь сильнее, счастливее, семьей и вес. Did you understand what I was saying?
Most of it, yes. Well, it was actually very important.
My sincere congratulations from your two supervisors. This took me a long time, but I did it, as I said, out of respect for you because of the person who you are. And I think I wish you, along with Andrew, good luck with all your future undertakings. And our final message is, do believe in yourself. And we bought some personalized presents. Andrew took care of it, I have to say. And he will now hand them over. Congratulations.
Well, I don't bring So this is for you. Oh, it's for you. If I try to translate what they say, you would never believe. Like, when I heard Andrew's speech, it was extremely cute, and I've never heard him this personal and encouraging. But then what Connie did for me was just a dive into the Russian, which is actually, it means much more than you could think from me, because you see there's no family members here, right? So it was very cute and very sweet of you. I'm so grateful for this moment of this connection to my home. And I could never make this way without you, especially you, Andrew. And especially the last few months, when you tried to kick me and finish this when I was really resisting this. Last few months, and this zigzagging was basically when you tried to football me in the right direction, and I was resisting, and you still football me, and somehow you made it really happen, and I will always be grateful for that very much. So yeah, this, I think we should stop before I start crying or something. Very good, thank you very much.